Okay, I think let us start. See, last class we have been discussing so far the stress components, and we have also seen the Hooke's law in 3 dimension, and there are many things, many other things which, like, we need to understand the relation between stresses, strain displacement, and also like compatibility equation to formulate the problem. Formulate in the sense, in advanced solid mechanics, this subject is quite analytical, theoretical. First we have to understand the concept, and then we establish some formulation. Okay, formulation, and then we can solve some examples, problems. Because it's a really complex situation where you are having 3 dimensional stress of stress, also stresses on any plane and all those things. So in today's class we are discussing, like, I'm just telling you the flow, how we have moved forward, where we began. Okay, first we have discussed about stress at a point, then like just the definition and the concept. Okay, and then we discuss about components of the stress in 3 dimension, and also we have seen like why we are calling stress as a tensor quantity. Okay, and then sign convention and the notations of the stress components. And last class we have been discussing about how you can replace. There are two things we discussed in last class. One is 3D Hooke's law. It was very simple, and then we established relation between strain on left side and stress on the right side. But I told you to work out on stress on left side and strain on right side. So has any student tried this? Because I told you to do that as a homework, right? Has any student tried this, or you are still working, or you will work on that? I can't hear anybody's voice. Has any student tried?
Ma'am, I tried, but got too much confused about it. No, equation part.
Okay.
I'm still trying.
Okay, you try. It is easy. It is not very difficult. Okay, and just maybe I can. If you can't do that, maybe we can discuss that in the class. I will show you how you can arrive at those formula. It is simply algebraic manipulation, but we will discuss maybe in the next class. So till next class, you may please try and we discuss. Okay, fine. So this is Hooke's law, and also we have seen that how are you replacing the stresses. Okay, we had 6 stress components, 3 shear and 3 normal. Okay, and how you are going to replace these in the form of stress resultant. Okay, that's the equivalent, because elasticity deals with stresses. So our starting point is stress, whereas in your strength of material, what your mechanics of material, what you have learned, you directly telling about, moment, shear forces and all those quantities, and then later on you are deriving the stress formula, right? So there the concept is like you are always talking about equivalent resultant force, not the stresses, but elasticity, because since we are discussing stress at a point, because the complex body we need to determine the stress is at a point, right? So I talk about stresses and strain first, and then if I integrate those stresses, I can replace those stress resultant. So those stress resultants are equivalent moments or equivalent shear forces, right? We have seen that you can replace with the either torque, you can replace if you consider x, y and z axis. Some forces may produce a moment, some combination of the forces produce torque, I mean the twisting moment, and some forces produce the bending moments, some produce stress resultant produces shear forces. Okay, so that document also I think I have shared in the, please check, keep on checking your teams, okay, that teams files, just go to files and all, where I will be uploading all class materials, okay, and then you may refer if you want to revise, please revise. So this is about stress resultant, that last class we have discussed that how you can integrate those forces, maybe tau xy, tau yx, yz or zx, and sigma x, sigma y, sigma z, you get axial force. Okay, I forgot to mention that there can be axial force also, we may call it N. Shear force, which is the vertical, axial force which is in within the axis, and we can also have the moments. So all three things, just go through that integration formulas very carefully and just try to understand the sign convention, directions, everything. So we have been doing so far, pretty okay. Okay, we are moving slowly, we have to move forward because this subject, first you need to create a background, okay, and then problems, like formulation and then problems, okay. So problem will come much afterwards. We have to understand some theories, there is a theoretical background, but this is very fundamental, so it is essential that you understand everything, okay. Now in today's class we will be discussing about strain, okay, strain and displacement components. So what are strain and displacement? As I told you that corresponding normal stress and corresponding shear stress is having corresponding strain, that we have, I think I have mentioned somewhere in the class while discussing Hooke's law. Okay, so if you are relating stresses and strain, that I know that epsilon x is your strain in the x direction, epsilon y is a strain in the y direction, epsilon z, and we had shear strain, that is xy, gamma y z and gamma zx. So these are the strain component. Now what are strain displacement relations? See, any solid body, when you are applying force. Now in civil engineering, structural engineering, we have our solid body which is constrained. Constrained in the sense, if you apply load, the body is under equilibrium. If you apply any load, then there will be internal deformation that takes place. Now it is because of that, because of what? Internal displacement that can happen. I mean this particle, if you apply load, this particle may shift to somewhere here, not at the original position. So there are deformations in the body that takes place. Now this deformation, why it is happening only within the body? So because all our structures, civil engineering structures are constrained. Constrained in the sense, अगर मेरे पास एक बीम है, उसको मैंने सपोर्ट किया है, okay, I have supported my beams and I am applying external loads. Now this beam, within the cross section of the beam, there will be a displacement. Okay, there will be, like if you look at the cross section, if you allow the deformation, the point, if you pick up any point within that cross section or the solid body, that point may not remain at the original position. It may it may displace to some other position, right? It is because we are constraining, means if there are roller supports, there are hinge supports here, and because this body cannot move from the supports, it cannot move from the support. अगर मेरे पास बीम है, ये सपोर्ट है, तो ये सपोर्ट पे वो मूव नहीं होगा, It may not displace on the supports, it may not displace on the constraint boundary. So we have constraint boundary, this is very very important. Why deformation takes place in solid body under equilibrium? Because there are external loads applied, that is okay. Under the external load there will be deformation, but why only internal deformation, and why only not the shifting of the body? If I apply force, it should shift from here to here, right? It is not shifting. What kind of shifting that we call? It is called as rigid body movement. Rigid body movement. What do you mean by rigid body? Rigid body is something you are applying force and it is, the body is not constrained at all. It is free, completely free. It is not constrained and you are applying the force. That means there is a rigid body translation. The body, entire body will move from one place to another place. But that will never happen in our case, right? Our structures are always supported something or the other on the support. They are always on the supports, always on the boundaries. So we call it is constraint, right? And if, because it is a constraint, if you apply force, there will be internal movement that will happen. And that is displacement. Why internal movement happen? Because we have constrained our body. आपकी जो सॉलिड बॉडी है उसको हमने सपोर्ट किया है, उसके वजह से अगर आप एक्सटर्नल लोड अप्लाई करते हो तो इंटरनल डेवलपमेंट मूवमेंट होगी, दैट इज कॉल्ड, वी कॉल इट displacement, and we are finding relative displacement components, that is called as strain. Now all of you have understood this delta L by L, but that was I am telling you that is for the simplest case, is how much is the change in the length, okay, that's all. So that is just delta L by L. Strain in the body is a relative displacement, but entire length, you know, आप ये जो ये है average sense में जाता है, it is not strain at a point. Now along with concept of stress at a point, I also need to figure it out strain at a point. Okay, so there is a concept strain at a point, and I need to know the displacement components in the within the body, right? And I am giving you reason why the internal movement happens, why strain develop, why strain energy. You must have heard about strain energy. We will discuss that in the 3D cases also. Why internal movements happens? Because body is constrained, it is not allowed to move outside. The rigid body translation is not allowed, because our structure, we may never accept that, right? Our structures are always supported, they are constrained, they are having boundary conditions, okay, everywhere. So that is the reason we need to investigate deformations. But how much deformations are allowed with respect to the external load? So deformations, we are, whatever in elasticity theory which we are learning, is deformations are small. There are small deflections. This is called small deflection theory, where I always have, like, you know, the deflection which is very small as compared to in addition to the applied loading condition. We don't want our structures to deform larger. Now there are class of structures which are non-linear, geometrically non-linear structures. Perhaps some of you may take the projects on that, you know, the larger deflection happens. Like आपने एक टेंट का वो देखा होगा, टेंट का जो रूफ है देखा होगा, वो कैसे, वो रूफ में अगर आप थोड़ा सा भी पंचिंग करते हो, आप उसमें लोड अप्लाई करते हो, द मटेरियल ऑफ दैट शीट इज वेरी वेरी थिन. If you apply load, it will have a larger deflection. Okay, so that comes under geometrically non-linear structures. Okay, that is not in elasticity. We are still considering geometrically linear. Linear meaning force versus displacement relationship should be linear. Linear relation. Okay, because P and delta is always in the linear. We have like that graph also, like you must have delta and P, or stress versus strain. So we have linear, and then you know, something like this. And we still follow basically Hooke's law. So non-linear structure, geometrically non-linear, will not consider in this course. Elasticity, we have geometrically linear. That means deflections are small, that is the assumption. But still we need to investigate the deflection. Most of you have designed the beams, you have checked the deflection criteria, you have designed slab. So deflection criteria are equally important. So in this subject we will find out the deflection, right? What is our final goal? We will find out stresses, we will find out deflections, but right now in this class what I need to tell you that how to relate stress, strain, displacement components. Now in any 3D body we have, like if you again take a one point, right? So just talk about that again, that there will be one point O, and that point O, deflection of this point O will be, when you apply force, this point will move to somewhere here, point O dash. Okay, if then the original coordinates of this point O is, let's say UVW, then it is shifting, that means there will be some change in the U will happen, V will happen and W will happen. So U dash, V dash, W dash. Now what are U, V, W? Those are the components of displacements in X, Y and Z direction. But because since we are discussing 3D, right? We are discussing 3D, मतलब वो लीनियर ट्रांसलेशन नहीं है, ये लीनियर ट्रांसलेशन में ये U एक डायरेक्शन में U डेवलप होगा, बट 3D के अंदर अगर मेरा ये एक पॉइंट इधर है, this is your X, Y and Z, if my original point is here, but when you apply load it will shift somewhere here which has three components. The displacement will be having, this is the line where 3D, in 3D body the deflections that has happened, point O moves from point O to O dash, then projection of these components on X, Y and Z axis. This is, we are calling the coordinates, basically coordinates of this point U, V, W. Those are the projection of displacement components on X, Y and Z axis. So this is the notation that in usually in X direction displacement component is U, in Y direction deflection component is V, and in Z direction deflection component is W. Now it is important to relate strain and displacement, but it is completely geometrical base. Now see, there is no Hooke's law here. When I derive the strain displacement components, it is purely based on geometry, deformed geometry. Okay, so we have to draw the deformed geometry and establish based on the geometry. अगर मेरा एक point displace हुआ है body के अंदर, then I have to define what you call, it's completely geometrical, right? You can just draw the diagrams, just show how the deformation has taken place, and I relate my strain and I calculate my strain and displacement. So let us try to investigate how you can derive those formulas for strain displacement relations in the 3 dimensions. So this was preliminary background that I discussed. Now let us try to just take first unidirectional, one direction, that is X direction में हम investigate करेंगे, but similarly you can think of in Y and Z direction. So first I will just draw the diagram where you just consider the simple case, but I am investigating strain at a point because I don't want that average, you know, that change in the length, total length, that I don't want. It's a total length. Delta L by L is the total length, strain in the total bar, right? I don't want that. So what I will do to derive strain at a point, we take help of always calculus. Okay, because everything, because we need to derive our formula which is applicable at a point level, I mean point, right? So what we do is simple, just consider 2 points. original without deformation. Okay, point A and B on this bar. So slowly we will derive those equation A and B. These are the original points. Now this body is subjected to some kind of force. This is consider, you can consider this as a solid body. Let us take this as x. Sorry, let us consider a small differential length. Small differential. आपको कुछ डाउट है तो मुझे बीच में पूछ सकते हो, हाँ, because it should not go one way. If any doubt, please discuss. Okay, I'm explaining you, but if you don't understand, please discuss. So this is small differential length. Why differential length? Because I want to investigate strain at a point. And then this axis is x-axis. From here to here, you can have it. Now this point, when you apply force, this point will shift to some other point. So let us have another diagram, which is a deform. Okay, deform shape. Deform माने अभी एक ही डायरेक्शन में हम इन्वेस्टिगेट करेंगे. Now this point, original point was here. This point has shifted somewhere here. So let us call A dash. And similarly, this point has shifted somewhere here. So let us call V dash. So new length is. Now how much is this new length? How much is this new length? If displacement originally here is u, then with respect to dx, how much is the change in the u, and how to determine that? We will take help of calculus. So I will give you a simple definition. This will be frequently used. So perhaps you must have studied this before. I have no idea, but you may recall. If you have studied, please inform me that you have studied this, or I discuss. Okay, so help of calculus. Everybody knows that function f dash x is equal to dy by dx. मेरा कोई भी फंक्शन एफ एक्स इक्वल टू वाई है, ओके, एनी फंक्शन. Now in our case it may be displacement function, it may be deflection function. You may call it u also. I mean y, only y. I can call u also, I can call w also, I can call v also, right? So function, this is from calculus point of view, derivative of the function is dy by dx. Now how much is the change in the function value? So you may observe here, change in the function is dy. Okay, change in the function is dy. Small change in the function's value. Dy is what? F dash x times dx. So this is dy by dx into dx. So what is the change? Small increase in the function's value. Function's value is what? Y. How much is the change? Dy. So it is according to this simple formula. This is called linearization in calculus. Okay, it's from mathematics. So, but we are engineers, so we should know how to use mathematics in a simpler language, right? So I am just discussing that part. We are not talking about heavy mathematics part here. Okay, we are discussing very simple formula, very simple thing. Then how we can use it for our purpose. Okay. So dy is equal to f dash x dx, dy is equal to dy by dx into. So small change. Now how much is the increase in the function? So in our case, when I want to write in terms of u, I can write in terms of u as du, change in the u. Small change in displacement function du can be written du by dx into dx. And then how much is the increase? Why dx? Because with respect to x. So here you may see with respect to x. जो चेंज हो रहा है वो विथ रिस्पेक्ट टू एक्स, मीन्स आप अगर डी बाई डी एक्स स्लोप लेते हो तो वो जैसे x बढ़ता है वैसे y बढ़ेगा, राइट? एंड दैट्स व्हाई वी आर कॉलिंग डी बाई डी एक्स. सो जैसे ही आपका x बढ़ेगा ऐसे y में चेंज आएगा. सो दिस डिनोमिनेटर dx इज बिकॉज ऑफ दैट dy by dx into dx. So here if I want to write in terms of u, I will write du is equal to du by dx into dx. That's a small change in the displacement function. Now it may be function money, it may be the function of x, y, z in our case. W may be function of x, y, z because it's a 3-dimension object, right? B may be function of x, y, z because it is 3D. If it is 1D, it's just function is fx, f of x. But if it is partial differentiation, then f of x, y, it's a function of x and y both. Then this y, right hand side also there are x terms and y terms and that type of function. So 3D elasticity, we talk about 3D functions, partial differentiation. Okay, now coming back to our point, how much is the increase? Increase मतलब original u है उसमें कितना बढ़ रहा है, तो d u plus du, and there du is how much? U plus du by dx into dx. So अगर मुझे यहाँ पे displacement change in the displacement function, if I want to write, I may write how much is the increase in the displacement. So it will be u plus du by dx into dx. Understood?
Yes, ma'am.
Okay. Okay, now this is about component. Just the component means u जो point है उसकी बात करें. अगर हम मुझे पूरे length की बात करनी है, how much is the increase in the length with respect to dx? So because u is displacing from here to another point, that is z. So increase in u is from b to b dash is u plus du by dx. But if I want to write the total change in the length, that is this length, instead of u I will write dx यहाँ पे. Okay, but change will remain same because it's the linear displacement which is increasing with respect to x, and it is in addition to the dx length. तो dx length के अंदर u के वजह से इंक्रीमेंट आएगा, तो ये जो सेकंड टर्म है du by dx, it will remain as it is. But first term अगर पूरी लेंथ को चेंज करके हुए लिखना है, then what I will write here, total length of a dash b dash will be dx plus del u by del x into dx. ये del u क्यों लिख रहे हैं? क्योंकि पार्शियल डिफरेंशिएशन आएगा, क्योंकि हम सिर्फ x नहीं y और z डायरेक्शन में भी लिखेंगे ये सारे इक्वेशन. So I am just mentioning del u by del x, okay, instead of du by dx. If it is one dimension, you may still write du by d. So how much is the change? See, how much is the component from d to b dash? It is simply u plus del u by del x into dx. But how much is change in ab to a dash b dash? It's the total length instead of u, क्योंकि पूरी लेंथ में कितना इंक्रीमेंट आया है, ठीक है, पूरी लेंथ में जो चेंज है, और वो किसके वजह से है? बिकॉज इज वी आर टॉकिंग अबाउट डिस्प्लेसमेंट इन एक्स डायरेक्शन. It is because of u only, right? So I made the second term won't change, so I will write del u by del x into dx. Okay, so length a dash b dash, length जो a dash b dash है, what will be that? A dash b dash will be dx plus del u by del x into dx. Now we use our simple definition of the string, okay, and then because we are talking about more generalized concept, so that delta L by L won't work, but definition won't change. स्ट्रेन का जो बेसिक डेफिनेशन है वो चेंज. So what is the basic definition of strain in any body? Final length, you must have studied this, right? Final length minus original length.
Delta L by.
Divide by original length, right? So final minus original हम क्या बोलते हैं? Delta L बोलते हैं और original length को हम L बोलेंगे. So that definition does not change, but हमारे केस में final length original length हमारा अलग है, right? It is not this. So this delta L upper in the denominator, what is that? It is final length minus original length. तो हम हमारी जो अभी लेंथ है, लेंथ AB, ओरिजिनल लेंथ हम dx बोलेंगे, ठीक है? And final length is a dash b dash. So I know that original length is, this is your a dash b dash, and original length is AB and AB. So I have the formula, I already have the formula. So a dash b dash is dx plus del u by del x into dx. dx plus del u by del x into dx minus AB, AB की लेंथ dx है जो ओरिजिनल लेंथ है, dx डिवाइड बाय dx. तो dx dx कैंसल हो जाएगा. This will go away, it's a negative, and this will finally dx into dx. तो ये भी जाएगा. फाइनली हमें क्या मिला? del u by del x. So ये हमारा एप्सिलॉन आ गया है. So we are able to actually derive the strain displacement component, which is for normal strain. Okay, this is for normal strain. Similarly, you may write now मेरी बाकी एक्सिस में y एंड z में, तो अभी हमने यहाँ जो u डैश लिखा था, ठीक है, जो चेंज है वो चेंज क्या है? u प्लस डेल यू बाई डेल एक्स इंटू डी एक्स. सिमिलरली v के लिए और सिमिलरली w के लिए. बट अगर मेरी y एक्सिस है, ठीक है, y एक्सिस में मुझे मेरा डिस्प्लेसमेंट कंपोनेंट v है, तो सेम वे में मैं आई कैन introduce normal. As long as normal strain is concerned, there is as such no issue at all, as long as normal strain is concerned. If it is just normal strain, it is simply a translation, right? So there is no confusion here. If you, because ultimately we are projecting the component UVW, we are projecting the XYZ component of that is UVW. So it's just already the normal translation, okay, and strain. So if I take y axis and I want y component, projection on y component, that is V. So strain in y direction, normal strain in y direction will be similar. So what will it be? That epsilon y. Okay, and what will be that formula according similar to this? I can't hear you.
Del u by del y. Del u del y.
Yes,
Del
yes.
V by del Y.
Yes, yes, very good. Del V by del Y. And normal strain in Z direction. So it is del W by del Z. So three normal